So we start.
Starting
Okay.
time.
Yeah.
Yeah.
So let us start the discussion session, please, Kirill.
Okay. Thank you, Roman. Unfortunately, the number of participants has decreased, but it's okay. This is hardcore, I believe. Okay. My suggestion is as follows. About 7 minutes, I will summarize and present some ideas, which we can discuss in general discussions. Then I will give to every speaker 5 to 7 minutes to present their ideas, and we can discuss them during a few minutes, and then after then there will be general discussion. Is it okay?
Yeah, sure.
Good. Then let's start. So I suggest that we, in general discussion, we concentrate on two big questions. First, what is the analog of three critical endpoint in finite systems? Our guesses are here, that surface tension vanishes, or drop of sigma meson mass, behavior of susceptibilities ratios, and other suggestions I will show on next page, just briefly. And the second major question is, what do we need to improve our state of art, related to my general question in my talk. Okay, so this is the sketch of results and predictions taken from Marek Gadzicki talk, which was, I believe, in October. And here you can see several pictures of different signals. Yeah, so there are several talks on at this conference. They discussed this kurtosis. Then there are these results of the proton intermittency. Then Professor Lu and Dr. Juan Torres Rincon discussed these very nice predictions. And there is also this difference in size between interferometer radii, but they're so small, I use the magnifying glass and I don't see them. But the whole point is that you see there are several predictions and each of them gives its own energy. So then the question is, what do we need for a convergence of our pictures and how to improve the state of the art? And I will try to argue. So, but in order to answer the second question, I think we should fix the present situation. My personal opinion, I do not pretend on much, is the following. From this conference and other meetings I took part, that our colleagues from FRG, Dyson Schwinger, and effector models are really doing a great job. And the point is that I even understand what they're doing. The astrophysics community is doing even greater job, in my opinion, although sometimes I don't understand what they're doing. And they really they produce beautiful pictures and movies. These are really pieces of the art. Also, I know that colleagues from analytical lattice QCD are producing very interesting results. But what about numerical or computational lattice QCD? You see, in 1984, I first studied the lectures on lattice QCD written by Yuri Makeenko. And those days, it was a general belief that lattice QCD will be a guide for phenomenology and for the experiment. However, as I see it for, let's say, last 15 years, roughly, numerical lattice QCD community is preoccupied with its own problem, unfortunately. To some extent, it helps to effective models, no doubt. but unfortunately, there are no relations to the experiments. And I think they can improve it. Numerical lattice QCD has a great potential. This is the picture from my talk, so phase diagram, and still I ask this fundamental question: what is the physical reason that the first order phase transition is terminated? Or if we put it other way around, what is the reason of crossover existence? You see, we just, how to say, we just see that it exists, but what is the reason? We are physicists, we should study. And as I told you, experiments do not tell us what is the surface tension, for example, at the supercritical temperatures. But lattice QCD could provide the great numerical experiment. They don't need to use just this hard lattice QCD. They could use fluid dynamics, where we do know that the phase structure, and there are exact results. They can use spin systems, which are much easier to study, also with quarks. And I believe, it is my personal belief, that if they introduce the cluster definition lattice, like it was suggested by Christoph Gattringer, and it was used in our works, they can find the clusters on the lattice through the Polyakov loop values close to the center of Zn group value, and they would be able to determine the surface curvature, Gaussian surface curvature tension coefficient, and their dependencies on temperature. This would be great. No one so far in the world can do this, but they can. Also, I think that they have great potential to come to experiments more closely, not only to our phenomenology. We should remember that in our heavy ion collision experiments, we have many jets, and the number of jets is increasing with the collision energy. Also, we have electromagnetic pairs going through our matter, even they very weakly interact with the strongly interacting particles, but if there are many of them, they can change the situation. For example, from experiments on irradiation of real liquids, we know that the surface tension coefficient of liquid decreases under irradiation. And there are experiments, probably you also know about them. And therefore, if it is the case and our jets are serving like this irradiation, then in experiments, the critical end temperature may be lower under irradiation. But how? Nobody knows. I think lattice QCD could help us. At the beginning, for example, the simplest idea is to introduce random defects on the lattice by turning the Polyakov loop or some quarks off or completely remove them. Then they can find the modification of state, which is really close to the situation in the experiment. And again, they could be helpful to us to find characteristics of the modification of such characteristics like surface tension, curvature tension, and other things. Because this is of fundamental importance. And also, I think maybe I'm dreaming, who knows, but the progress of computer technologies is very fast. Maybe soon we will have real quantum computer, and then in a few years, I hope that lattice QCD will be able to go from static equation of state to real simulations of transport of partons. These are my suggestions. And now I would like to ask, are there other suggestions for lattice QCD, other opinions? If there are brief, please let us tell us. Otherwise, we can go further. Okay, Nugzar, please.
I have an answer to the first problem or question which you put it. Why first order transition exists?
No, physical reason. Why? Physical reason,
Yes.
not just. Okay.
If I have a few minutes, I will answer. If later.
I could be brief.
Okay. Let us change slightly the question. Let us describe precisely the phenomenon, and then obviously we find answer. What is the state before the endpoint of first order transition? We have either liquid or gas corresponding simultaneously, right? At one region or mixture somewhere. Two component system. They differ exactly in what sense? When we have some resolution power, we say, oh, gas contains point particles and there are some distance. With this resolution, we cannot identify that liquid contains constituents. It's a 2 or 3 dimensional body, right? These two phases differs by dimensions, integer dimensions. For point particles, you have 0 dimension by definition, as you mentioned, topological definition. They are only integer valued. And for liquid, we have 2, or if you like, 1 or 3, really 3 dimensions. At the point of the end of first order transition, we have something like vapor containing that balls of the water and balls of the gas and mixture, which is described precisely by fractal dimension as a clothes. It's a standard example.
Yes.
So we describe mathematically this process of transition from the first order region to the end point by one parameter, by dimension of space, which in that points becomes non-integer fractal and may change continuously, more or less. This is the precise description. How it this is answer.
How to measure it experimentally? You see, that's the point.
Experimentally, precisely that in the first talk was done. You have definition of dimension, measure the number of water points in the inside of this fractal structure, count them, and measure the dimension. It depends on material pairs. So how to measure is obvious. But the theoretical point is, this is the precise description of experimental picture of phenomenology, if you like. How to reformulate this existence in the theoretical terms, or formulate mathematical model and then understanding, theoretical understanding. This is easy to do for me, but needs some time, some definitions and so on. Okay. So I will stop here to save.
Okay, thank you. Thank you. It's an interesting point. For me, it is very hard job to solve a model analytically, but okay, we can also do it. I
can show you.
partly agree with you. Okay, then other opinions or suggestions? Short one, please. Nugzar was rather brief, I have to say. That's very good. Other? I do not see. Then this general question, let's discuss from Natalia Cala to Sidorin about the Goa room. Will you construct the second additional cluster to Goa room and so on? The question is written here. Do you see my screen? Roman.
Yeah, sure.
Okay,
We can see your screen. It's not a problem.
Can someone answer? For example, Professor Rogachevsky or Anatoly Sidorin. Natalia, Sidorin answered
Yes,
the question.
yes.
Could you comment, please?
What?
Could you tell us his answer to us?
Yes, he answered that it's really planned to build 2 additional clusters on territory of Laboratory of High Energy Physics, and more additional information may be found on the site of the NICA project. So
Okay.
I think this is enough.
Thank you. Then we go to the input from Professor Luo. Professor Luo, are you around?
Yeah, you see, we probably have some technical problems because we do not have actually Anatoly Sidorin and Oleg Rogachevsky now, so I'm not sure. So,
But how about Professor Luo?
yeah, he's not here either. I cannot see him. So maybe it's some kind of technical problems. I mailed it now, but I do not have an answer yet.
Okay, then we can return back to this talk. Dr. Juan Torres Rinken, are you around?
Yes, I am.
Okay, then the stage is yours. I stopped my screen, but then I will return to it. Oh.
Okay, so maybe I should share the same slide.
Yeah, this is your slide.
On my screen, so that would be, and I should do it bigger. Oops. Yeah, so in fact, I prepared this slide also, because Professor Xiaofeng also mentioned this problem, but now he is not around apparently. So I don't know if it's really some expert that can, answer this question.
Yes.
But okay, let me introduce the question for the discussion. So, well, as I explained in my talk, and also in previous talk, we look at this ratio of yields, triton, proton, deuteron. Yes, and I also propose new ratios, including helium-4. But of course, we would need a solid baseline for this ratio where there are no critical effects, no signs of the phase transition. And then I saw these 2 results, but there are many others. This one in the left side is the statistical thermal model, and the one in the right is coalescence model. I think one of the latest results. So then you observe in both is this flat, the baseline. I mean, in both of these, they are not considering effects of critical point, but you see the flagged dependence, which is nice. But now the difference is the value. I mean, here's this value of this ratio is around 1. Here is around 0.3, maybe 0.4, depending on the process. There is this difference here. We would like to understand. Of course, there are so different models for like nuclei production, but we would like to understand a little bit. And then if you dip a little bit into the difference, well, you will realize that the problem lies in the triton yield, and this was also mentioned in the first talk. And in particular, if you look at the star data of ratio, in this case, it's ratio of triton yield over proton, for example, or even deuteron. So this is the middle panel, right-handed panel here. You will observe this difference with respect to the thermal model. Yeah, thermal model is over predicting this production of triton in intermediate energies. So then my question is a bit both people doing statistical thermal model, both experimentalists, but what could be the origin of this puzzle here, and how can we improve in this description of the baseline? So in fact, I have no idea. I mean, I can tell you that the experimental data also has some assumptions because it's working with the blast wave model, which is extrapolating multiplicities in PT domains, which are not measured. So this is also so it should be good, but it's also an assumption. So, okay, I don't know if somebody has some idea of why the reason there's this difference in multiplicities.
Is it all? Juan, is it all?
Yeah.
Yes, okay.
Yes, I'm still here, but I don't know if somebody has some idea or.
Okay, about the Triton, I can tell you, you see, the model to which people refer is very primitive and actually, I mean, thermal model, yeah? So I think we can improve it with our more sophisticated model.
Yeah, well, I didn't say, but this thermal model here is not the same as the statistical model by Bovchenko. It's different one.
Yes. Yeah, because I remember these are results, I think it is from the 2011 paper where they used ideal gas, actually. For nuclear, you cannot do it, okay? You should include the virial coefficients, even the classical one, and then you can get better description. But the point is very interesting. Now, has anyone questions to Dr. Juan Torres Rincon? Please raise your hand and ask him. Yeah, please, Nugzar, but be, be brief.
Very brief. I have comments, so it will be not so brief. So I postpone.
Okay, then I have a couple of questions. Let me share.
Yeah, let me stop sharing my screen.
Yes.
Kyrill, I have also a question.
Yeah, okay. Dima, I have not seen you. Who is it?
Yeah. May I ask?
Sure.
So it's some delay. The question about nicely it was shown nuclear potential in the Valechka-Sirot model with sigma and omega, and sigma then was considered with decreased mass, but at large distances, for instance, for description of deuteron, pion exchange becomes important. And my question is, was somehow pion exchange taken into account? And pion exchange also in medium modifies. So why, if you consider large distances, not to take into account pion, which is the most far distant object? Thank you.
Yes, thank you. Yes, in fact, we consider to take into account the one pion exchange in the nucleon potential, but in fact, for these ideas around the critical point, we didn't need it. In any case, the one pion exchange is attraction, gives you an attraction at even larger distances, as you said. So in any case, that will help for this attraction between nucleons, and essentially the mass stays constant as a function of temperature approximately until it gets degenerate with the sigma close to Tc. So in any case, I mean, it's something that is always a positive contribution to this attraction. Like it's not going to change the result, the main result.
But then maybe further question that when you decrease the sigma mass, the effective coupling constant of sigma, coupling constant divided by the mass, which ends to equation of state. For sigma, becomes stronger than that of omega, and then instead of repulsion which you had at small distances, because in usual Waleshko models, omega is more repulsive and more strongly repulsive to explain small distance repulsion in small distances. Then you come back come to attraction, because your sigma becomes more attractive than omega repulsive. And in the same, then you have with pi, because pi is attractive. So the role of pi, in some sense, becomes more closer to the sigma when sigma mass decreases, isn't it?
It is.
Yeah, so there are different things concerning the coupling itself. We play also with the couplings to reduce the coupling same amount as the mass and whatnot. But the point is that at finite temperature, we had no more insight how the coupling of this sigma to the nucleons behaves close to the critical point. Does it have a critical exponent, or should be some non-universal value? So with the mass, we know that should go with some particular critical exponent at first order, but the coupling was a bit not clear. So we play a little bit with that, but we didn't have a good model for that. And concerning the omega, that I can see that there is a question here with the omega meson
my
as well.
questions, yeah.
Yeah, so should I answer the two of them?
Please.
I will start with the omega one, because it's related to the previous question.
Yeah.
So the assumption that we do is essentially that the omega meson will also have modifications in the mass, but it's not compensated by the decrease of the sigma one, because the sigma one is the one connected to the critical mode. And unfortunately, I don't have a backup slide, but if I can share my screen, I can show you backup slide of a different talk where I will also answer the first one with that particular slide. So let me see. Okay. I have to share this.
Professor Voskresensky, are you satisfied?
Okay, thank you.
Yeah, let me show you this. Yeah. I mean, maybe, I don't know if this is can help, because this is in some effective model, this is PNGL model, where you can compute the masses, thermal masses of pion, sigma, omega. Then you observe here that the omega mass, which is you have to focus on the blue line, the dashed blue line. So this one here, because this is the one that passes through the critical point of PNGL. It also has modifications, so it decays the mass of the omega as well, but it doesn't go as much reduction as the sigma. So somehow, of course, it modified. Yeah, here is the numbers. It's not compensated by that. So that was a bit the motivation for just considering the sigma especially. And now, very fast, concerning the first question was about how about the decay width of the sigma meson. Yes. This is an important question, because if you identify the sigma field with the resonance that appear in 2 pion scattering in S wave, well, we did this exercise here. This is we consider the nucleon potential, when you consider not just a stable sigma, but the whole spectral function. The spectral function of the sigma, which is broad state, was taken from FRG calculation using quark meson model, and then we computed this potential in this way. It's a bit more complicated, but you take the full spectral function of sigma. And then you see that the results are slightly different, but this is the comparison with a stable sigma and full spectral width at different values of sigma, and then, or different temperatures if you want. And then we observe with that similar results. You have some kind of oscillations due to the numerical method, these integrals here, but essentially you can ignore this spectral width.
Okay. Then very good answer. Yeah. One more. Nugzar, is it short?
Short.
Okay. Please stop sharing for a moment.
We see at that slide, the last one, that the minimum, we organized minimum by 2-component potential, sigma, and at the size of 1 Fermi, sigma omega. At this minimum was
Next one.
Oh, it's not
this one.
this here.
We see that it is less than 1 Fermi, but more than half Fermi. Can we organize maybe edit fine potential also the minimum at the size of 5 or 10 Fermi?
Yeah, very good. But to what physics does it correspond?
Exactly. We have very nice physics of halos of the light nucleus.
Yeah, large nuclei, not helium. Sorry, not helium.
Not helium. Actually, lithium-11, for example.
Oh.
They are in halos far from the center, or distances order of 10.
Maybe, but we are talking about the nuclei with less than 5 nucleons so far. Please. Okay, the question is interesting, but is not related directly to this.
Question is, can we organize by this realistic mechanism components the minimum at the size of 5 or 10 Fermi? This is question inside of the talk, but the request was why, and I answered why. But question does not ask the.
Can I iterate on this question?
Yes, David, please.
This question
mention hypertriton, okay?
There's also this question of so-called alpha matter or of low density isomer of nuclear matter. Maybe this is related then to a corresponding effective potential which would have a pocket at larger internucleon distances. I just want to bring this in, which is related to the appearance of clusters in the nuclear matter. Alphas are bosons, they can condensate, and there is always this idea, or was always this idea around of an alpha condensate matter, where the effective potential then has a pocket, and in the phase diagram we have low density isomers, a second minimum in the energy per nucleon curve.
Okay.
Yeah, I mean, if I can just comment briefly,
yes.
Just to say that here I presented the most simple model that you can think, which is this Valecka with 2 different contributions. And of course, here you can just go to and do some more sophisticated studies. Of course, I didn't want to say that, I mean, if you study nuclear structure, of course, there is very sophisticated ways of creating the nucleon-nucleon interaction via effective theories. And then you can do more sophisticated and much more detailed studies. So yeah, here I presented just the simplest version we can do.
Yeah, thank you. Are there any more questions? Yes, I also have suggestion. Are there any questions from the audience? Okay. It's very interesting research direction, but the question is, you could apply your nice prediction to hypertriton ratios. Exactly. So, and this is coming back to Nusgaard question. Usually we consider that the size of this hypertriton is something like between 8 and 10 Fermis. So it is huge, and minimum is very shallow. And probably if you apply your arguments, you will see that hypertriton will not exist at the one vicinity of the critical endpoint. This might be a certain prediction. What do you think about this?
I mean, your suggestion is very interesting. In fact, I have some ideas how to continue to this
okay,
in the strangeness sector. Of course, you have to derive some similar potential for hyperon nucleon, for example, and in this case, nucleon-nucleon and nucleon-hyperon. And maybe you find also modifications of this potential close to the critical point that will give you more bounded hypertriton.
Yeah, another
molecules.
Yes. Just a moment. One more suggestion. Probably you can ask Jan Pavlovsky about the couplings. They have many results. Maybe they also have this coupling to nucleons, or it's not hard to calculate them.
For this exercise here, I think they don't have. This is the coupling to nucleons.
Yeah.
And I didn't touch it. This is here. It's just the same.
But probably they did not calculate. They were not interested. But maybe you can ask them.
Because you know this sigma couples to the quarks directly in this model.
Yes.
But maybe you're right. Maybe you can do some scaling analysis to see how it couples to nucleons.
I don't think it is very hard. Okay. Comment from Nuxar. Or it is just by chance?
It was old.
Okay. Then please stop sharing screen. We go back. Thank you to Dr. Juan Torres Rincon. These questions were answered by him. Dr. San, are you around? Do you see my screen? Probably not. Dr. San. Kai-San, are you around? Okay.
We have Stefan Lu now. I mean, he returned. He had some problems with connection, probably. And,
okay.
Now he's here. So you skipped answers, questions to him. I mean,
you mean Professor Lu?
Yeah.
Okay.
Professor Stefan Lu, Stefan, can you hear me?
These are your questions. Then I turn on my screen. Okay, so you have 5 to 7 minutes, please. You can go through your slides you did not show, or you can go to the discussion. Okay. Thank you.
Okay, there are some left slide. I think. Thank you, organizer, to give me this opportunity. So
your mic, please check your mic because it's not like perfect. Your audio is not perfect. Please check your mic.
Microphone.
Yeah, your microphone.
Can you hear me now?
Yeah, we can, but it is not loud enough. Okay.
How about now?
Okay.
Okay, so let me continue that. This slide, and actually a STAR experiment has measured not only net proton fluctuation, but also net Keon and net charge, which net Keon is used to approximate to net strangeness fluctuation. However, you can see left the data point actually with large statistical uncertainties. This is basically due to that the width of the distribution of the net charge is much larger compared to net proton, and also the net Keon has lower efficiency. That's why they got larger uncertainty. So if we want to make a more precise measurement to this two, we need to higher statistics. So in the BS2, it may help. And also from some effective model that predict that indeed if near close to the critical point that the baron sectors has larger fluctuations compared to charge and strangeness. This is mainly due to the mass of the strange quark is much larger than UD quark. The coupling actually depends on the mass of the quarks. Till now that STAR has measured these two interesting phenomena structure in these two observable. One is that you see this non-atomic energy dependence of this net proton fluctuation, the fourth order, and also the yield ratio of the light nuclei. And one interesting thing is that they both see some anomalous behavior around 20 GeV. You see here is the deep structure, and here is the peak structure. And also there are the values have sudden changes. I mean jumps between 19 this 20 GeV and 14.5 GeV in both observable. So In STAR collaboration, we have proposed to take one additional energy, which is at 7.1 GeV, with mu b around 266 MeV. With mu b about 235 MeV, which is just in the middle of this 14.5 and 19.6 GeV to confirm whether indeed this jump is real. And also from Torres Rican's talk that I think we need to whether we can understand these two structures simultaneously. I mean, in the same physics with the same physics origin, and they actually have some so-called the pre-cluster formation and modified NN potential. That could possible explanation of those structures happening at a similar energies. And we could also measure even higher order, for example, 6th order or 8th order barrel number fluctuations. For sure, those higher order barrel number fluctuations could be more sensitive to the critical fluctuations and the correlation lengths, and also close to the critical temperatures, you can see that their higher order barrel number conservation, their values are starting to become negative. And this sign change will be also a good signature of the Kyrill crossover in the future if we have enough statistics to say that there's negative sign of those high order fluctuations. Yeah, and also at high mu b region, you can see for future low energies heavy ankylations, because in the fixed target experiment or collider experiment such as NICA, that we may collect enough statistics to perform precise measurement for this higher order barrel number fluctuations. There are also some model predictions, their values. That also can be validated or tested. Yes, STAR experiment with current data, we have measured also the 6th order barrel number fluctuations as a function of the collision centrality for two energies. One is 54.4 GeV and the other is 200 GeV. Sorry, 200 GeV. And for 200 GeV, we see that as a function of the collision energies, it seems like that as a central collisions, the value of 6th order barrel number fluctuation is negative, while at 40.5 GeV, it's positive, which is different from the 200 GeV. And also lattice QCD calculation performed at the mu b equal to 0 have shown this negative values for both 200 GeV and 54 GeV. And one caveat of that is that currently, due to the limited statistics, we don't have enough statistics to perform this most central, for example, 0 to 5% or 0 to 10. We just use the 0 to 40% centrality, just combine several centrality to report this result. So actually, if we report the most central one, 0 to 5, the error bar will be much larger. So obviously, in the future, we will accumulate more statistics to measure this higher order fluctuation. Yeah, actually, the second phase of the Beamer scan is very important. It will focus on the energy below 20 GeV. And we already, since 2019, we already have finished this second phase of the Beamer scan of several energies from 19.6 GeV down to 9.7 GeV, 9.2 GeV. This 4 energy has already been successfully collected with high statistics during 2019 and 2020. The data analysis is still ongoing, so we will hopefully we will report the results soon. This will actually reduce the statistical error bars of those data points below 20 GeV. You see, currently the error bars are still large. and reduce to the error bar will shrink to the green band. And whether we will see a peak at low energies, so it's very crucial to perform the measurement between 2 to 8 GeV, I would say. And this is energy ranging that covered by NICA, CBM, and future CEE, which will be built in China. And to complete the QCD critical point search, for example, this predict signature of the critical point, see this monotonic oscillation behavior. Currently, at energy below 20 G, we still have large uncertainties.
Okay, thank you very much for your interesting conclusions. So, short questions, please. Are there? I don't see so far. Okay, if not, then I have questions because time is running. Please stop sharing your screen.
Okay.
And we shall ask you a few questions. First, these questions to you. This is my question and my students. So you as a famous experimentalist, could you tell us what is the wrong with this anti-triton in Alice experiment? You see, these are very high energies, proton-proton, lead-lead, triton they measure, this attracts, and anti-triton they do not. Do we understand right that this is experimental problem? Because anti-triton, yeah.
Yeah. So yeah, I'm not an Alice member, so
yes, I know.
And,
but
from physics-wise, actually, those light nuclear production will decrease when you increase the energies.
Mm-hmm.
Because based on the coalescence picture, you need more nucleons or baryon densities to coalescence into those light nucleus. At such extreme energies, you have baryon density is very low at middle rapidity, so you have a less chance.
Mm-hmm. Okay. Now the second question about this nice ratio which you discussed and Juan Torres Rincon, triton, proton, deuteron square. What about antiparticles? Are they also interested or not?
Yeah, that's a good question actually. That for antiparticles, we don't have much statistics to.
Yes, unfortunately.
Yeah, for example, anti-triton.
Yeah, this is why I asked you. You see that they are related.
Yeah,
of course.
it's almost impossible currently. They are
okay.
Very low. Yeah.
Okay. Are there any other questions to Professor Wu? I don't see. So, David, do you have any question?
Yes,
okay.
Very short one. I was interested in this fixed target program. So sorry if I did not follow that point. You mentioned that you have already taken data, or what is planned in terms of the data taking program? At which status we are? When will we hear first results from the fixed target?
Can I share screen?
Yeah.
Thank you. Actually, we have making progress, and you see here in the backup slide, I put here that this is planned. The left side is collider mode. We have collected those energies, and the black one is already taking in BS1, and the red one, which is will be taking in BS2. And 7.7 GeV, the collider will collect the next year. And for fixed target mode, actually we already have in 2018, we already taken the about more than 200 million events, about 3 GeV with mu v value 700 MeV also, and you can see that those all fixed target energies that have in the year taken. Actually, we have taken a lot of fixed target data, but you can see we have so many data collected. It takes time to calibrate and also generate. So it takes time to analyze everything. Those are data points we have collected.
Yeah, I had heard from Daniel Zebra about the plans, but therefore I was curious why there was no results reported yet. Mm-hmm.
Yeah, actually, it's very due to I would say due to some calibration issue and short of manpower. You see, even the BS2 data, for example, 19 GB BS2 already taken, but still in processing, it produce those data yet. We don't have chance to analyze because the calibration is not finished yet.
I'm also asking because this could, of course, if there were already some indications, yeah, this could have a good influence also of the program which is to be started soon at NICA. Yeah? Therefore, I wish you good luck. And when do you expect some first results to be released?
Hopefully earlier next year.
Okay.
Yeah, because many data sets have been taken.
Okay, thank you.
Okay, gentlemen, we should thank to Professor Lu for a very nice presentation and sketch of the result, but time is running. I do not see Professor Rogachevsky around, so then we can stop this session. If there are some comments, Nugzar, I'm sorry, we do not have time. Comments,
but if
sure,
I have no time.
Yeah, we have to stop already because next session will start.
Okay.
A very short question is allowed.
Okay, the last one.
That concerns a question which was raised in the chats and then was said to be clarified personally, but I'm interested in it. It is the question about the capacity of the Goroun computer, in particular what concerns NVIDIA. Maybe somebody around in the audience can also answer this. And
maybe, but not me, definitely. Okay, if there are no...
Yeah, we don't have now probably anyone from GNA, so probably no one is around now, unfortunately.
Okay, then I will ask this also in private. Then.
Okay.
Thank you.
Then, thank you, David. Thank you, Roman. Then on the behalf of all organizers, I'm thanking to speakers and to participants of this discussion for a very interesting one. And I hope that we will learn some hard lessons, and probably in a couple of years, we will come with the right theory, and then we will have chance to discover the critical endpoint experimentally. Thank you very much.
Okay.